This is a review of quadratic functions. It's the longest topic in 2D, so it spans chapters 4 to 6 in the textbook. For that reason, we might have to do it in a couple different parts, so we're able to upload it to YouTube. If you recall, at the end of chapter 4, we made a very nice foldable that goes through all of the topics from chapter 4. So I highly recommend that you find that and that you refer to it when you're studying for this section of your exam. I will go through some of the topics in that foldable today, but I'll do them briefly, just as a reminder, not as kind of a reteaching of those topics. You can refer to your foldable to help you with that. So how do you recognize a quadratic function? There's 3 different ways of identifying or recognizing a quadratic relation. So the first way is by looking at a graph, and that's probably the easiest way to recognize a quadratic is by looking at its graph, because the image of a quadratic function on a graph is a parabola. Now, parabola is basically a curve that is completely symmetrical and it follows the step pattern. So we'll talk about that in a moment. I'm going to draw a couple here. This one opens up and this one opens down. So parabolas can be smiley faces or they can be frowns. They can open up or they can open down. Now let's talk about the things you need to know about a parabola on the graph, or the graph of a quadratic function. Let's take a look just at this parabola right here that opens down, and I'll use it as an example to discuss the features. A parabola specifically is a graph that's symmetrical. It has to be symmetrical. It has to have an axis of symmetry that goes right through the vertex of the parabola. So this here is called the axis of symmetry. And it goes right through the vertex, which is the very middle point of the parabola. Let's give our vertex some coordinates right now, just hypothetically. Let's say this is 2, 5. So if this vertex is 2, 5, that means this is 2 on the x-axis, this would be 5 on the y-axis, then our equation of the axis of symmetry would be x equals 2. So your equation has to always use the x coordinate of the vertex, and it has to start with x equals. A couple other points you need to know on the parabola. You need to be able to identify the x-intercepts. So there's one right here, and there's one over there. Those can be referred to as x-intercepts. They can also be called roots or zeros, because at that spot y is equal to 0 for that function. A parabola can have 2 x-intercepts or 2 roots. It may, however, also only have one if the vertex lies exactly on the x-axis, like that one right there. Or it might not have any at all if the parabola is somewhere down here and never crosses the x-axis. So just keep in mind it could have 0, 1, or 2 x-intercepts. You also need to know where the y-intercept is, which is the same thing as a y-intercept for a line, so that should be pretty easy for you. Y-intercept is the spot where it crosses the y-axis. Now the vertex tells us the equation of the axis of symmetry, but it also tells us another important feature. When you look at the parabola and you see that it opens up or down, that gives you either a highest or a lowest value that that parabola can have. The highest or lowest y value is called the maximum or minimum. It's the optimal value. So at the vertex, this is the highest it's ever going to go. It's the highest the y value is ever going to get right there. That's called the maximum value. And the maximum value is going to be always the same as the y coordinate of the vertex. So this 5 right here is what we use for our maximum value. If the parabola opens up, it's not going to have a maximum, but it's going to have a minimum value. If this vertex right here were -3, -2, then the minimum value would be equal to -2, because it's always the y coordinate of the vertex. So the first way you can recognize a quadratic function is on a graph. It is a parabola when it's graphed. It has an axis of symmetry, a vertex, 0, 1, or 2 roots, a y-intercept, and it also has an optimal value, which is either the maximum or the minimum value. Now, a parabola is special because it follows a step pattern. And a step pattern is kind of like the slope of a line, except it's a step pattern because it's changing. Quadratic functions don't have the same slope. If you look at the slope down by the vertex, it's a lower slope, it's more gradual, and as you continue on, it gets steeper and steeper and steeper, and then the opposite direction as well. So there's no such thing as a slope of a parabola, but we refer to it by its step pattern. Now the step pattern is 1, 3, 5. It's odd numbers. Step pattern here, I'll put it down, is 1, 3, 5 times whatever the a value is in the equation. So if, for example, the equation were y equals 2x squared, the a value is the number in front of the x squared, so it would be the 2. So instead of having a step pattern of 1, 3, 5, we would double it. We'd say 2, 6, 10. So the way the step pattern works is when you start at the vertex, you always go over by 1. So your step pattern goes over by 1, and it goes up or down by whatever the steps are. So if my equation was y equals 2x squared, it would go over 1, up 2, over 1, up 6, over 1, up 10. A negative a value, such as y equals negative 4x squared, the negative 4 would mean that it goes down instead of up. So that's how you can tell how to plot your points on a graph. The next way to recognize a quadratic function is by looking at its equation. So the equation has 3 different forms. There's 3 forms. And the equation can look like this. It can be y equals ax squared plus bx plus c. So for example, y equals negative 2x squared plus 3x, or y equals 4x squared minus 2x plus 1. Those are examples of equations in standard form. That's the first form. Standard form, that's the first form of a quadratic equation. And standard form is special because it allows us easily to read the y-intercept of the graph. The value at the end all by itself is your y-intercept. So in that first example right over here, we noticed there was no y value by itself at the end. There was no c. There was an a and a b, but there was no constant term at the end. That means that the y-intercept of this parabola would be equal to 0. In this case over here, we had a 1 by itself at the end. That's our c value. So the y-intercept of this parabola here would be 1. From standard form, we can also tell a lot of things about the direction of opening and whether the parabola is stretched or compressed. The a value is the number in front of the x squared. In this case, it was a negative 2, and over here it was a positive 4. The a value tells us the direction of opening. If it's a negative number, it'll open down, and if it's a positive number, it'll open up. As well, it tells us the stretch or compression, so the higher the a value, the thinner the parabola will be, and we'll talk about that when we talk about transformations in a few minutes. The second form of a quadratic equation is a vertex form. So vertex form is the form that allows us to easily read the vertex of the parabola right out of the equation. So it looks like this: y equals a bracket x minus h squared plus k. When we're creating an equation in vertex form, we can't forget about the squared sign. That's the most commonly missed part of that equation. Also note that there's a negative sign in the bracket, so that's going to require us to change signs when we take the vertex from the equation. So the vertex is going to be your h and your k values. So h, comma, k is the vertex of that parabola. An example of an equation in vertex form could be y equals 2 bracket x minus 5 squared plus 2. So this equation here gives us the vertex positive 5, because we changed the sign, positive 2. That's the vertex of that parabola. From the vertex, we can also read the equation of the axis of symmetry. So x equals 5 would be the axis of symmetry equation, and the maximum or minimum value. Now it's the y-coordinate of the vertex, but I know that it's a minimum value because this positive 2 tells me it opens up. So its minimum value is going to be 2. If I gave you the equation y equals negative 4x plus 3 squared, the vertex of that parabola would be negative 3, 0, because there's no number where the k is in the general form of the equation. Likewise, if we looked at y equals 2x squared plus 5, there's no number in the brackets, so the vertex of that quadratic function would be 0, 5. The third form of the quadratic equation is factored form. And factored form allows you to easily read the roots or the x-intercepts of the parabola from the equation. So it looks like y equals ax minus rx minus s. There are two brackets, and in each of those brackets we can read our roots. So again, we change the signs. So our roots are r and s. And from an equation such as y equals 2x minus 3x plus 4, we would read that the roots or the zeros would be 3 and negative 4, because we remember to change the signs when they come out of the brackets. So you'll need to know the three forms of quadratic equations: standard form, vertex form, and factored form. But when you look at any equation in general, you can tell it's a quadratic equation because its highest degree is 2. It's a second degree equation. That means that when you look at the x, you find the variable, the highest exponent that you'll see on that variable is a 2. It'll be an x squared. If the equation does not have x squared in it, or has an x cubed or more, that means it's not a quadratic equation. You see that in standard form, the x squared is right there. In vertex form, the x is in the brackets and the whole bracket is squared. And in factored form, you have two brackets and you're multiplying an x in each bracket, which would expand to x squared. So quadratic equations are second degree equations, and that's how they can be identified when you're shown an equation. That's how you know it's going to be a parabola when you put it on a graph. The third way of identifying a quadratic function is by looking at its table of values. So a table of values is going to give you the x and the y's for a bunch of different points on the graph. We'll make an example here to show you how you can use that table of values to tell it's a quadratic function or not. So let's say that the x coordinates were from 0 to 4, and the y values that correspond were -2, -3, 0, 7, and 18. You can tell that a table of values is that of a quadratic relation or quadratic function by completing your finite differences, by looking at first and second differences in that table of values. So the first differences column goes right after the y column, and it's the result of subtracting successive y values. So basically you take the bottom y and you subtract the top y. It's the change in the y's. So -3 minus -2. Be careful when you have negative numbers. So you're subtracting a negative. This means you're adding, right? Minus a negative means you're adding. So you're going to get -1 as a change. The way of seeing that is, okay, well, I was at -2. What happened from -2 to -3? I went down 1. From -3 to 0, what happened? Well, I went up by 3. And 0 minus -3 would give us that +3 answer as well. From 0 to 7, we went up by 7. And 7 to 18, we went up by 11. So those are the first differences. If you look at your first differences column and you see that the first differences are equal, that means it's a linear equation or a linear relation. So first differences are equal means it's a line. If the first differences are not equal, then you can calculate your second differences, which means you're going to do the bottom first difference minus the top first difference, just like we did for calculating the first differences. And you're going to say, okay, what's the change going from -1 to 3? Well, I went up by 4. From 3 to 7, I went up by 4. 7 to 11, I went up by 4. If you wanted to show the calculation, you would write down 3 minus -1, and that would give you your 4. 7 minus 3 would give you your 4, and 11 minus 7 would also give you your 4. If you calculate the second differences and they are all the same, see how they're all 4 right over here, that tells you that it's a quadratic function. So if the second differences are equal, then it's a quadratic function. The important thing to remember when you're going to use first and second differences to tell the type of function that you're looking at is that it has to be when x goes up by the same number each time. So if x is going up by 1 each time, then you can say, okay, since x goes up by the same number, if the first differences are equal, it's linear. If the second differences are equal, then it's quadratic. If you skipped steps in your x, or if your x increased by 1 and then by 5 or by 7, then you couldn't necessarily count on the first and second differences without finding the missing parts of your table to see if they were the same or if they were different numbers. So as long as x increases or changes by the same number each time, it could be x decreasing by 1 each time or by 2 each time, then you can use the first and second differences to tell if the function is linear, quadratic, or if it's neither. If neither the first differences nor the second differences were the same, then it wouldn't be either linear or quadratic, it'd be something else, and then you just say it's neither. So we're going to stop here and we're going to continue in a second part talking about how to describe transformations of parabolas. So when you're looking at the graph of a parabola,